Imagine a traveler arriving not from another city, another country, or even another continent, but from an entirely different planetary system, a silent wanderer that crossed unimaginable distances, drifting through the interstellar void for millions of years, until celestial chance brought it into the domain of our sun. This traveler exists, and its name is 3IATLAS. Few celestial objects in recent memory have attracted as much curiosity and scientific attention as this one. Every new observation, every spectrum recorded, every light curve analyzed reveals a little more about its origins and nature. And the most recent discovery is something no one expected to detect so clearly from an object so distant. Changed everything. Water escaping into space. Water from another star system. This discovery not only confirms its cometary nature but opens an entirely new frontier in comparative astronomy. For the first time, scientists can analyze water activity in an interstellar comet using the same framework used for comets born within our own solar system. Today, we explore in detail how this discovery was made, what it reveals, and why 3IATLAS may become one of the most important interstellar visitors in scientific history. Designated as the third confirmed interstellar object to pass through our solar system, 3IATLAS follows in the footsteps of Oumuamua and 2I. But unlike these fast-moving predecessors, 3IATLAS offers astronomers an unusual opportunity. Its trajectory allows us to observe it for far longer, rather than a brief appearance followed by a rapid departure. 3IATLAS has been tracked as it approached the solar system, monitored as it moved among the planets, and will continue to be observed as it leaves us behind. This provides a rare full-arc dataset of an interstellar visitor. Comets, whether local or interstellar, ancient archives. Their icy materials preserve records of the environments in which they formed. Studying an object like 3IATLAS is like reading a chapter from the history of another planetary system, written in frozen molecules carried across the galaxy.
The moment astronomers realized that 3IATLAS followed a hyperbolic trajectory, that it was not gravitationally bound to the Sun, the scientific community mobilized. Ground-based telescopes, space observatories, and specialized instruments adjusted their schedules. If Earth was being visited by an object from beyond our cosmic neighborhood, every available tool would be used to study it. Early results revealed something unexpected. 3IATLAS was active much farther from the Sun than typical comets. Its coma and faint gas emissions hinted that something unusual was happening, something that did not match the standard behavior of comets from the Kuiper belt or Oort cloud. But to truly understand what was occurring, astronomers needed a specific kind of observation, one that only a space telescope could provide. NASA's Swift Observatory was originally designed to study high-energy events, such as gamma-ray bursts. But the spacecraft carries instruments capable of observing ultraviolet radiation, making it an excellent tool for studying comets. Why ultraviolet? Because ultraviolet observations can detect a very important molecule, hydroxyl O. Hydroxyl is formed when sunlight breaks apart water molecules. Therefore, where there is hydroxyl, there was water, and where there is water, there is cometary activity. Earth's atmosphere blocks most ultraviolet radiation, so detecting hydroxyl from the ground is nearly impossible. Swift, orbiting above this shield, can pick up the faint signatures coming from comets, even distant ones. When astronomers pointed Swift at 3IATLAS, they hoped to catch even the slightest trace of activity. What they found was far more significant.
The ultraviolet spectra returned by Swift were unmistakable. 3IATLAS was releasing large quantities of hydroxyl. This could only mean one thing: water ice on its surface was sublimating under sunlight. This discovery marked a scientific milestone. For the first time ever, researchers could use standard comet analysis methods on an interstellar object. It was now possible to compare, in detail, how water-rich 3IATLAS is compared to solar system comets. These comparisons may one day reveal whether planetary systems across the galaxy form under similar chemical conditions, or whether each system is shaped by unique environments. But the most surprising result was the sheer amount of water being expelled. Swift's observations determined that 3I-ATLAS was losing 40 kilograms of water per second, equivalent to the output of a full-power firefighting hose. This rate is remarkable for any comet, but what makes it extraordinary is its distance from the Sun at the time. 3 astronomical units, 3 times farther than Earth, well beyond the region where water ice commonly settles. Typical solar system comets remain mostly inactive at this distance, yet 3I Atlas was vigorously venting water. Astronomers have proposed several hypotheses. Its surface may contain fine-grained ice that sublimates more easily. Its outer layers could have been disrupted by microimpacts during its long interstellar journey. Its chemical composition may differ fundamentally from the comets of our solar system. It may have undergone heating and cooling cycles in a very different stellar environment. Whatever the cause, its behavior is not evidence of artificial origin. It is simply the natural diversity expected from a body born around another star. Differences do not imply mystery, they imply history. Each interstellar object carries a story written by the conditions of its birthplace. Detecting water from another planetary system is far more significant than it may initially seem. It proves that water ice forms commonly beyond our solar system. It provides clues about the chemistry of distant planetary nurseries, and it allows researchers to study whether the volatile materials that helped shape Earth and the planets exist widely throughout the galaxy. The implications are profound. If water is common in other systems, could the ingredients for life also be widespread? How many worlds might have oceans, clouds, or icy surfaces? How similar or different are they from the planets of our own star? While the answers remain unknown, discoveries like those from 3I Atlas bring us closer to understanding the cosmic context of life. In certain periods, public interest spikes when observers can no longer see the comet. Some speculate about secrecy or technical failures, but the explanation is simply orbital geometry. Recently, 3I-ATLAS passed behind the Sun relative to Earth. When this happens, the Sun's glare blocks observations from our telescopes, regardless of their power. There is no shutdown of instruments, no attempt to hide data. It is merely celestial mechanics. As soon as the comet moves into a safer observation angle, telescopes will resume tracking it. As 3I Atlas approaches and then passes its perihelion, the closest point to the Sun, its activity will change. Scientists expect that water emission will increase as the comet heats up. Its coma and tail will undergo structural changes. Sublimation may expose new layers of material. Comparisons between pre- and post-perihelion activity will reveal internal composition. The Swift telescope, along with ground and space facilities worldwide, is expected to participate in a global monitoring campaign. These observations could provide insights impossible to gain from any comet native to our solar system. 3I Atlas has now joined a very exclusive class of objects interstellar visitors that reveal their internal chemistry. Each object observed enriches our understanding of how planetary systems form, how they evolve, how objects are ejected across the galaxy, and how common water and potentially life-related molecules may be. By studying 3I Atlas, we are learning not only about an isolated comet, but about the diversity of planetary systems throughout the Milky Way. As we watch water vapor escape from 3I-ATLAS, we are witnessing something extraordinary. Molecules that originated around another star, formed in another era, shaped by another world. This water is not from our Sun, not from our planets, not from any process familiar to our solar system. It belongs to a distant corner of the galaxy, and in observing it, we expand our understanding of what lies beyond the boundaries of our home. Each new data point, each spectrum, each measurement is a step toward unveiling the chemistry, structure, and origins of planetary systems scattered throughout the cosmos. 3I-ATLAS is not merely a comet, it is a message in a bottle sent across the stars, carrying the story of its birthplace. And its brief passage through our skies has given us a rare chance to read a chapter from a book written far beyond our Sun.